Okay, just before I start this lesson, just a mention of this website. This is betterpasspapers.com, which just gives you a nice, easy way to access Leaving Cert papers. I wouldn't wait until sixth year to start looking at all Leaving Cert papers all the way through fifth year. You know, our plan in fifth year, remember, was to complete the ordinary level course. Go through some of these, look up some old Leaving Cert papers, give them a go. So in this class, I've taken a question here from 2007. This is from the 2007 Leaving Cert paper. This is 2007. It's an ordinary level question. It's question 4 and it's the B part. Okay, and it ties in nicely with what we're doing at the moment. And it's to do with Newton's laws and connected particles on slopes. So that's what really I'm going to be looking at in this class, is particles on slopes connected. So let me read through the question. It says a rough plane is inclined at 30 degrees to the horizontal and has a smooth light pulley attached to its uppermost point. A taut, light, inelastic string passes over the pulley and has masses of 3 kilos and 2 kilos attached to its endpoints. The coefficient of friction between the 2 kilogram mass and the plane is 1 over root 3. The 3 kilogram mass hangs vertically. The system is released from rest. The 3 kilogram mass moves vertically downwards. Okay. So a couple of things to know just in the question. A few key details in here. You know, it says a rough plane, so we know this friction involved here is inclined at 30 degrees. So we've got friction happening on this inclined plane along here. There's a smooth, light pulley. Smooth meaning no friction, light meaning the mass is negligible, we don't have to worry about it. Attached to its uppermost point. A taut, light, inelastic. Light meaning mass is negligible. Inelastic means it's not stretching up or down, it's fixed length. The tension throughout the string will be constant. It's taut, it's not loose, so it's not going to suddenly, this isn't going to suddenly drop and then snap the string and create an impact or a collision. It's just something running smoothly. Every time the 3 kilogram mass moves down, the 2 kilogram mass will move up. Okay. The coefficient of friction between the 2 kilogram mass and the plane is 1 over root 3. So we have friction because the plane is rough. That's the coefficient of friction. That's determined by really the kind of materials that the plane and the mass here are made out of. And the 3 kilogram mass hangs vertically. It's not in contact with anything. A more difficult question would be to have, you know, maybe a vertical wall here at which and the 3 kilogram mass is in contact, and that would create other issues with friction. That might be a higher level question. The 3 kilogram mass moves vertically downwards. Okay, we'd nearly guessed that. Question says, you know, show on separate diagrams all the forces acting on each mass, find the common acceleration, find the tension in the string. So that's what we're going to try to do. So, even without the first kind of part, which is really just a hint telling us what we need to do in order to solve for the second and third parts, we're generally going to solve questions of this type by drawing force diagrams. So the first thing I'm going to do is draw a force diagram for the system. Okay, so generally give it a little heading there, force diagram. And there are two particles, so we're going to have two force diagrams. We're going to have a force diagram for the 2 kilogram particle on the inclined face, and we're going to have a separate force diagram for the 3 kilogram particle. Remember, with force diagram, make sure to give each object, each particle within the question, a separate diagram. We don't want to do them all together, and only include forces that are, you know, acting on that particular particle. Okay, so let's draw the force diagram for the 2 kilogram particle and see if we can figure out some stuff. So the 2 kilogram particle is on an inclined face like so, and there's my picture of my particle. So what forces are acting on this particle? And there are a few. The first, most obvious force I always think about is the force on the object by gravity. And the force on the object by gravity is called the weight of the object. And the weight of the object is always its mass multiplied by little g. So in this case, it'll be 2 multiplied by little g, where little g represents the acceleration due to gravity. The other force at work on the 2 kilogram particle, there it is, it's on the inclined face. So anytime two objects are in contact with each other, we have what we call a contact force. The contact force is called the normal reaction here, and it's a normal always means at right angles to in maths. The normal reaction is always perpendicular to the plane here, so it's going to be the normal reaction of my force diagram is perpendicular to the plane, and that's called OR. I'm just going to call that OR for normal reaction. The other force at work on the 2 kilogram mass, well, there's the force on the object by the string, and we call the force on the object by the string, that force is called a tension force. So I've got a tension force working up along that direction. And then finally, there is friction because the inclined face is rough, and we're going to have a friction force opposing motion down here. So we're going to have a friction force over here. Now, in order to calculate the friction force, we need to know the normal reaction. In order to know the normal reaction, we have to do some stuff with this second, this vector over here. Okay, I'll come back to that in a moment. Let me look at the 3 kilogram particle, and let's just look at the forces at work on this particle. Okay, much simpler. The only forces at work on the 3 kilogram particle are the force on the object by gravity, which is called the weight. Remember, weight is always equal to mass times little g, where g is the acceleration of the object due to gravity. And there's also a force here on the 3 kilogram mass by the string, and the force on an object by a string is called a tension force. So these are my force diagrams. That's them. They're completed. Okay, those are all the forces acting on these 2 particles. So make sure you get your force diagrams correct. Now, in order to think about the normal reaction and friction, I am going to resolve this. You should probably, think about doing this separately. Those are 2 lovely force diagrams. Maybe draw them separately, this one out separately, resolve the forces. I'm just going to resolve them in here on this one, but maybe, this is part 1 in the question. Call this part 1, move on to part 2, copy that out again, and resolve the forces there. I'm not going to bother with that. I'm actually going to go straight in and just resolve the forces right in here. So, tension and friction are parallel to the plane. They don't need to be resolved. The normal reaction is perpendicular to the plane. It doesn't need to be resolved. But this 2g, this weight force here, is kind of not perpendicular. It's not parallel. We're going to resolve it into its perpendicular and parallel components. Okay. And one thing, again, we've covered in class, at this stage, you should know that this angle in here is always going to be the same as the angle of inclination of the plane. And that's a little simple geometry. Make sure you can figure out why that is. So that's going to be 30 degrees in there. Let me get a thinner pen and write in 30 degrees. So that's going to be a 30 degree in there. So that's a little 30 degree. I don't know if you can see that, but just remember that angle in there is 30 degrees. Okay. So that angle in there is 30 degrees. I just write it in here. 30 degrees. Okay, so that's a 30 degree angle in there. And that tells me, that little resolved triangle, this little triangle here I'm using to resolve my 2g vector, is a 30, 60, 90 triangle. Okay, not brilliantly drawn, but you get the idea. It's a 30, 60, 90 triangle. And if we know our ratios of our sides in a 30, 60, 90 triangle, the sides are in the ratio 1 is to root 3 is to 2. In other words, the side opposite 30 is always half the hypotenuse. So this is going to be G. And the side opposite 60 is always root 3 times the side opposite 30. This is going to be G root 3. Okay? And those ratios are unique for 30, 60, 90 triangles if this angle wasn't 30, we'd, or 60, we'd have to resolve these in a different way. Okay, so there are my force diagrams. I've resolved all my forces. I'm ready to start thinking about my force equations. Before I do, I'm going to just think about a couple of, I suppose, important details here in my force diagram. One thing is I want to think about positive and negative directions. So what directions do we think are positive and negative? Well, this force diagram over here, we think in our system, in fact, we're told that the 3 kilogram mass moves vertically downwards. But even if we might nearly guess that. So if that's going to go downwards, accelerate downwards, I think I will decide that that's going to be a down positive system for that one. But if that's moving downwards, the 2 kilo has to move upwards. Remember, the string is taut and inelastic, so it has to move upwards at the same rate. So I'm going to make that direction positive for my 2 kilogram particle. So in my force diagram, this is going to be my positive direction for my 2 kilogram, and this is going to be my positive direction for the 3 kilogram. We say down positive for the 3 kilogram. Okay. The next thing is to think about force equations, or, to think about, I suppose, if I look at this particle, the 2 kilogram particle sliding along this plane, it is not going to accelerate away from the plane perpendicularly. It's not going to accelerate into the plane perpendicular. It's just moving parallel to the plane. Because there's no acceleration perpendicular to the plane, that means the forces up perpendicular to the plane must be equal to the forces down perpendicular to the plane. And that tells me, something about the vertical forces here. So let's look at our force diagrams. I'm going to start with my perpendicular forces over here for my 2 kilogram particle. So perpendicular to the plane, there's no acceleration perpendicular to the plane. The only acceleration is happening parallel to the plane, which means the force up away from the plane, the normal reaction there, must equal to the force down into the plane, which is going to be g root 3. G root 3. So that's the normal reaction. Actually, we have a value for the normal reaction, and that's a constant. The normal reaction here is g root 3. The other thing we're going to think about is this friction force. So I have to think about friction force. One thing to remember, friction is defined as being, well, I suppose the maximum friction is defined as being mu times r. So that's the maximum value that friction can reach. Now, if the object is in motion, as this is, well, all the friction is being used to try to stop that motion. All of that maximum friction is going to be used. So I'm trying to look at all this maximum friction, mu times r. So we're going to calculate mu times r. So friction force is going to be mu. Remember, mu is given. It's 1 over root 3. That's the coefficient of friction, times the normal reaction, which we've just worked out as g root 3. 1 over root 3 times g root 3, well, that's g. So the friction force is just going to equal to g. Now I'm ready to investigate the forces parallel to the plane. Okay? And this is, we have to be a little bit careful here, because tension is pulling up parallel to the plane, friction is pulling down parallel to the plane. But down here, look, there's also this component of the weight force that's pulling this down parallel to the plane as well. So if I look at my positive forces here, which are positive, well, my positive direction, I've decided, is up to the right. So tension is positive, which means my negative forces are friction and this component of the weight force. So my net force, remember, we're going to be using F net equals ma. The net force is always equal to the mass of the object times acceleration. That's what we're going to be using here. So the net force, well, T is my positive force because of the direction I've chosen to be positive. And then this g is a negative force, so we're going to subtract g. And then this g will be a negative force also. So we've got tension, subtract 2 of these g's, is equal to the mass of the object 2 times the acceleration. Simplifying, there just gives me t subtract 2g is equal to 2a. And I'm just going to give that equation a name for the moment. I'm going to call that equation number 1. Okay? T minus 2g equals 2a. There are two unknowns there, the tension and the acceleration. Looking at the 3 kilogram particle, okay, those forces I should have said were for the 2 kilogram particle. Looking over here at the forces on the 3 kilogram particle, well, this is a much simpler system altogether. It's down positive, so the positive force is 3g, the negative force is t, which means the net force will be 3g subtract that t. And that's equal to the mass times the acceleration, where the mass is 3 times the acceleration a. And that's just kind of as simple as I'm going to make that. That's equation number 2. Okay? So we've got two equations, two unknowns. We can solve these. This is a little system of equations and two unknowns. We're looking for values of a and t that satisfy this equation, but simultaneously satisfy this equation. So we're going to try to solve the system. I'm going to just rewrite those over on a new page so I have a bit of room to find everything out. So I'm just going to rewrite those two equations and solve everything from there. So let me just rewrite these two equations. So equation 1 and equation 2. Equation 1 says T, the tension force, subtract 2 times little g is equal to double the acceleration. And equation 2 says that 3g subtract t, that tension force, is equal to 3 times the acceleration. Okay, so this is what we've done. We've taken all the information we've gathered from the words and from the picture. We've drawn a couple of force diagrams. I had to resolve the forces here. I was able to calculate the value of the normal reaction. It's equal to the perpendicular component of the weight vector. From that normal reaction, I was able to calculate the force of friction, which is always the maximum friction will be mu or. If the system is in motion, well, then all the friction is being used. Then I was able to come up with my force equations parallel to the plane. I got 2 minus 2g equals 2a. Second system, much simpler. Positive force 3g, negative force t, net force 3g subtract t equals mass times acceleration 3a. So this is where we are at this stage. Okay, from here on in, everything is just straightforward algebra. I'm going to use the addition property of equations, which says if equal properties are added on both sides of the equation, then the two sides will remain equal. Adding here like terms t added to negative t, well, they cancel out, can be 0. 3g added to negative 2g, or negative 2g plus 3g is just 1g. 3a plus 2a, well, that's equal to 5a. So g is equal to 5a. Solving this equation using the division property, if both sides of the equation are divided by the same quantity, then the two sides remain equal. I'm going to divide by 5 to find a single acceleration. So therefore, the acceleration of the system is equal to g over 5. And the units will be meters per second squared. And that's my solution. That's my solution for part 2, which was to find the acceleration. Okay. Now, just a small note, at ordinary level leaving cert, they take g to be approximately 10. At higher level leaving cert, they take g to be approximately 9.8. But at ordinary level, we take g to be approximately 10, which would mean that a is approximately 10 over 5, which would be 2 meters per second squared. Okay, so at ordinary level, that's what we would say the acceleration is. At higher level, you know, leave it as g over 5 or plug in 9.8 there either. Okay, which will give you, I think, 1.96 or something like that. Okay, the third part is to find the tension in the string. So finally I want to find the tension in the string. Well, how do I do that? Well, I pick an equation. I'm going to pick equation number 1. And I'm going to just make tension the subject of this equation. How do I do that? Well, I use the addition property of equations, which says if 2g is added on both sides of this equation, then the two sides will remain equal. So adding 2g on both sides will give me 2a plus 2g. Okay. Taking a to be g over 5, we can solve from here. So we can say, well, t is going to be equal to double g over 5 and plus 2g. So that's going to be 2g over 5. Well, 2g is 10g over 5, and adding those two fractions together, that will give me 12g over 5. That's my tension. That's newtons. Okay, 12g over 5 newtons. Again, if we take, say, g is approximately 10, well, I can plug that in. That would give me t is equal to 120 over 5 newtons. Okay. If we take, I should say, approximately equal to there. So if we take g to be about 10, well then 10 should be about 120 over 5, which, you know, that simplifies to, I think, 24. So the tension would be 24 newtons, and the acceleration will be 2 meters per second squared. Okay? So go through that, you know, make sure you understand all the parts. There are 3 parts. Part 1, we had to find, draw the force diagrams. We draw them, resolve them. We had to work out the reaction force. Well, there's no acceleration perpendicular to the plane, so the reaction force has to equal to g root 3. Then parallel to the plane, tension force is the positive force. There are 2 negative forces, not only the g. Don't forget this component of the weight vector. That g is also pushing down to the left. So we've got 2 of those g's pushing down to the left. Really common error. So t minus 2g equals 2a. And then this much simpler affair over here. Down positive system. 3g is the positive force. T is the negative. 3g minus t is the net force. That has to equal to 3a. And then you're just solving the system. Some basic algebra. Make sure you can follow each step, okay? So A is about 2, T is 2 meters per second squared, T is about 24 newtons. So this question corresponds with 5e on our course, which is Newton's laws and connected particles on slopes, on inclined planes. So practice lots of that stuff. Keep working. Remember to post any questions, let me know, and I'll endeavor to answer them. Okay? Keep working, practice. Thanks.